Okay, we are talking about traffic flow theory, which gives you relationships between different traffic parameters. There are three main traffic parameters which we have talked about: mean speed, flow rate, and density. Okay, mean speed can be space mean speed or time mean speed. The space mean speed is the one which we use in the equations. Okay. And time speed is used as well. We have used it in the traffic engineering course, the spot speed, as the spot speed. So if you take speed of the vehicles, take their simple mean, that is time mean speed. If you take the speed of the vehicle as distance upon time, or you take the harmonic mean of the speeds, then it becomes space mean speed. Okay. Then we looked at different approaches of traffic flow theory. We have macroscopic approach and microscopic approach. Macroscopic approach, you are looking at the entire traffic flow, and microscopic approach, you are looking at how vehicles are following each other. You are looking at one vehicle or a pair of vehicles. Then we are now discussing different methods in macroscopic approaches. Macroscopic approach. So we have talked about how flow, density, and speed are related to each other. What are the equations between them? We looked at some of the equations. And these equations are given by two different guys. Both of them are Greens. Okay, one is Bruce Greenshield, the other one is Greenberg. Okay. The equation which was given by Bruce Greenshield, we have studied it in the traffic engineering course as well. It's a linear equation between speed and density. This one. Okay. So we have used this equation in the traffic engineering course as well, the linear equation. And if you have, somebody gives you the data, you can make your own equation like this. And what do we call this analysis? What is the name of this analysis? Huh? The method is called calibration, but making this equation a linear equation. Linear regression. Okay? Linear regression analysis. Okay, so in linear regression analysis, we already have this form: y equals to a plus bx. So you have any linear equation, you will have some y, you will have some x, you will have some a and b. For a and b, we know how to calculate that. After you made the equation, then you will find out r square, and r square tells you what? The accuracy or yes, they call it the fit, goodness of fit. Okay, how equation is fitting the data, how closely equation is fitting the data. Okay, and r square for a good equation should be close to what? 1. Sorry? Yes. More than 0.6. 0.6 or more. Okay, we looked at a couple of equations. This one, the equation was given, we found some parameters. The previous one, the data was given, we made about an equation. Now the problem is, sometimes the data will not have linear equation. Okay. All types of data does not follow y equals to a plus bx. Okay, then what do we do then? We already know that Greenberg has a model which has a natural log in it. This is a Greenberg model. Okay, so according to Greenberg, the speed and density have this relationship. So if somebody gives me the data and he says, I want to apply the Greenberg model on it. Okay, then how do I perform linear regression in that case? Because Dr. Onev only taught you linear regression. You don't know anything else. Huh? Right or wrong? So it's my mistake. Right? You should know it. There was a whole course about the statistics. Okay? But the way you guys are looking at me, I know you don't. Okay. But there is a way by which we can do linear regression even for a non-linear equation as well. Okay? I'll just give you the example for this model because this is the one which we have. But you can get the idea for any non-linear equation, you can play around with it to make it into a linear regression equation. So what did they do here? This was the actual equation and there's a natural log in it. Because of this natural log and there's a natural log in it and the variable is part of the log. What are my variables? What are the things which are changing? Speed and density. Okay. So the speed obviously one side of the equation, no problem. But density is part of the log. This is my problem. Okay. If it was only log kj, now what is kj? Jam density. Jam density is a constant. Okay. Whatever the constant is, I don't mind. Log kj, exponential kj, it will be a constant value, right? Whether you take log or exponential or a square or whatever, I don't mind. Okay. So my problem is this k which is inside the log. Okay. C is again a constant. Okay. So C is not my problem. Kj is not my problem. Both of them are constant values. My problem is this k which is part of the log. So what do? We expand this term. Okay. So C log kj upon k can be expanded to this thing. Okay. So it can be now expanded to this thing. Now this whole thing becomes what? It's a constant. C is a constant, kj is a constant. Constant multiplied by constant, yes? Constant. So this whole thing becomes, if you compare it to this equation, it becomes A whole was a constant, right? So here A was something, whatever, but here A means C log of kj. Clear? Okay, so I expanded the term, so I can have constants on one side. Okay, and then I have C log of k. C log of k. So what is the constant here and what is the variable? C is a constant, right? C is a constant. Okay, so B is this thing. Okay, A is this C. What is X? X is log of k. X equals to what? X equals to what? Log of. Clear? Clear? So you can play around. What was my aim? My aim was that whatever the term is, the variable, it should be separate. Either it is multiplied by the constant and then you can add a constant. Okay, this is the only thing we can do. For regression, this is the only thing we can do. You can multiply with a constant or you can add a constant. Okay, here it was divided as well. So to avoid this division, I expanded the term. Okay, so when I did this, my x becomes this whole thing, log of k. Okay, now you compare this with this. So this whole thing is a constant, which is b. This is multiplied by x, which is c. Okay, and x itself is log of k. Got it? Yeah. Okay. Now you will do it yourself, okay? You know how long it takes, right? You remember. You forgot. It will come in the exam. Okay. Now what is given here? It's the same exam for everybody. Huh? Why are we doing it here? Yes, it will come in the exam, he is looking at it. You will also get the same exam. Okay. What did they observe? So this is the data, and from this data we have to make the equation. Okay. Which equation? Not the green sheet equation, the Greenberg equation. You have to make the Greenberg equation. Okay. Because they are saying find out the regression constants of the Greenberg model. Okay. Okay, what are the constants of the Greenberg model? This thing, okay, and C. Clear? So I want this thing and this. Or Kj and C, simple. Kj and C. If I can get Kj and C, then I will get the coefficients. Okay. So I can take it as a regression equation, okay, and I can try to find out A and B like I did here. Okay, so I have an equation for A, I have an equation for B. Okay, my A is C log of Kj and my B is C. Okay, but to do this, I have to perform an extra step here. If you look at the data, what do I have to do with the data before I start calculating A and B? Before that. Now look, I need to do something with the data before I start finding out A. Yes. What is my x? Log of k. So the first thing we have to do is what? Convert this into x. This is k, but my equation doesn't have k. It has log of k. Okay? So your x will be log of k, not k. Clear? Clear? Log of k. Okay, my x is log of k. So first of all, from k you have to find out the values of x. Okay, and then you will repeat the whole procedure which we did earlier. Okay. Okay. We are not doing it. We are doing it. Because you have to take the log and then. Huh? ln, natural log. Natural log. Because you have to find out the natural log and then you have to find out A and B. That's why. Okay, you do it, you come up with it in the next lecture. Okay, come up with it tomorrow. Okay, the A and B values, give it to me tomorrow. Okay. Sorry. No bonus. This semester has no bonus. Okay. So the A and B values and the R square value. Okay, if you want, you can do the plot as well. But from the A and B values, we have to find out the coefficients of the Greenberg model. Okay, the regression constants of the Greenberg model, the C and the Kj. Okay, so once you find out A and B, then you can find out C and Kj. So come up with the A and B values tomorrow. Okay, otherwise this will remain as it is. We will not solve it. When you get a bonus 0 in the exam, maybe. Okay, clear? Okay, so tomorrow come up with the values of A and B. Okay, basically come up with these values: C log of Kj and C. This is your A and this is your B. Clear? And your X is log of K. Okay, so this is up to you. I see you. Give it to me tomorrow so we can solve it further. Okay. Then we are moving to the topic of shock waves. Okay. Shock wave is a phenomena in traffic which happens when you reach a segment or a point which has increase or decrease in capacity, a sudden increase or decrease in capacity. Okay, so the traffic flow approaches a point where the capacity suddenly increases or decreases. So this reduction or increment in capacity creates a phenomena which is called as shock wave. And the point at which this happens, this point is known as a bottleneck. Okay? There? You have the bottom in your hand. Very good. Huh? Okay. Usually the term bottleneck indicates reduction in capacity. When we say bottleneck, it means reduction in capacity, but because of the bottleneck, right? So smaller part of the bottle. Okay. So bottleneck usually refers to reduction in capacity, but shock wave can happen both ways. If you meet a point, if you come to a point where there is a sudden reduction in capacity, it will create a shock wave. If you come to a point which has a sudden increase in capacity, again it will create a shock wave. Okay, so increase is usually not called as bottleneck, but the phenomena is the same. Where can it happen? For example, there is a crash on the road, an accident on the road. Because of the accident, some of the lanes are blocked. Okay, or because of anything, some of the lanes are blocked. Maintenance work, construction work, car broken down, whatever. Okay, so if because of any reason the lanes are blocked, it will create a bottleneck. It will create a reduction in capacity. Restricted bridge sizes. So you have a bridge, and because of the cost of the bridge, you made the bridge. Usually, size of the bridge is less as compared to the lanes on the ground, because on the ground we have low cost, the bridge has higher cost. Usually size is less. Work zone, meaning what? What is the work zone? Construction, maintenance work. Okay. A signal turning red. So you reach a stop line, the signal turns red. Capacity becomes what? Capacity is how much? So the signal is red, capacity is 0. Capacity is 0. Okay. Okay. So now you see here two curves are given. This one, the normal condition. Okay. So you can see the curve is between flow and density. Flow and density. So you can see for the top curve, the maximum point is C1. What do we call this point? Capacity. The maximum point of the curve is what? Capacity. So in the normal condition, the highway has this much capacity. But a portion of the highway is affected because of a work zone, maybe because of a crash, maybe because of anything. Okay, so there is a part on the same highway which has a bottleneck. Okay, capacity of the bottleneck is less. So the bottom curve indicates that part of the highway which has a lower capacity. Okay, you can see the maximum point is here. Obviously, the shape of the curve cannot change. The trend between flow and density cannot change. Only thing changing is the numbers. The shape of the curve is same. Okay. Now let's say you have flow Q1. The initial flow is, let's say, Q1. Okay. Q1, it will reach the bottleneck. Before the bottleneck, it is on the normal part of the highway. Okay. So Q1 and the density is K1, which is a very low value. Okay. Now what will happen when you reach the point where there is a bottleneck? Okay. The flow is still how much? Q1. But look at the capacity of that bottleneck. Capacity is? Yes. So what will happen now?
Q.
The Q. How much flow can I have in the bottleneck? Capacity. Okay. So if this is the condition that the initial flow is more than the capacity of the bottleneck, then the flow which will pass through the bottleneck is equal to its capacity. So that flow is Q2, which is equal to capacity. Clear? So what will happen at Q2? Now you can see the density is this density. Okay. So you can see the flow has reduced. It was Q1, right? Q1 was higher. Now it has reduced to Q2, which is lower. But Q2 is equal to the capacity of the segment. So the density is higher. The flow has reduced, but the density has increased because the segment is smaller. Getting the point? Okay. Q1 was more, but the segment was also bigger. So the density being vehicles per mile. Okay. So since you are providing more space, so vehicles per mile were less. So density was here. Okay. Then you did what? You took all these vehicles and put them in a smaller segment. Okay. So now these vehicles cannot move. So your flow is less from here to here, but your density is more because all these vehicles are now jammed. Clear? Okay. Now what happens if the initial flow is Now what will happen after the bottleneck? So from Q2 it will move. Okay. Q2 will move forward, right? Once the bottleneck is finished, then again we have the normal part of the highway. Okay. So there was the normal part of the highway, then the bottleneck, and then again the normal part. Now which flow will reach in the next part? Which flow will reach in the next part? Q2, right? Okay. Now Q2 is this much. Q2 is here, right? Normal part, which curve is for the normal part of the highway? This one, right? Okay. So when you were in the bottleneck, you are here at this point. Capacity, high density. When the same flow will reach the normal part of the highway. You are back to this point. Okay, so your flow is same as before, but your density is
Yes.
okay. So now you took less vehicles and give them more space. Okay, so these things, when you go from here to here and then from here to here, what is this? Shockwave. So this is one shockwave and then this is another shockwave. When you are moving from here to here, this is one shockwave, and when you move from here to here, this is another shockwave. Okay, we will look at the names of these shockwaves. Okay. Okay. Now what will happen here? What is happening here? I have Q3. This is another flow. It has nothing to do with Q1, Q2. Q3. Okay. Q3 is in the normal part of the highway. Okay. Its density is K3. Okay. Then this flow enters the bottleneck. This flow enters the bottleneck. Will there be any change in flow?
No.
In the first case, there was a change, right?
Yeah.
Why is there no change now?
Because the flow is less than capacity.
Because the flow is less than capacity. So even in the bottleneck, the flow will continue. But do we have the same traffic conditions?
No.
No. Why? Because density is higher. We have the same number of vehicles, but their space is less. So I can maintain the number of vehicles, but I cannot maintain the density. Okay. So even though the flow is progressing without a stoppage, but the density increases, that means the speed will decrease. Okay, so the traffic conditions will change. The traffic conditions will change. Okay, so this is what they are showing here. Q3 in the normal part of the highway, Q3 in the bottleneck. Okay, so there is a difference between them, and again it will move to the normal part. Okay, so the density is changing, that means the traffic conditions are changing. Okay. Yeah. If you take the slope of the speed density curve at any point, if you take the slope of a speed density curve at any point, it will give you mean speed. This is normal. Take the slope of a speed density curve, it will give you speed, mean speed. Which is speed? Which mean speed? Space mean speed. Okay. When there is a shock wave, okay, so when there is a shock wave, then you take the slope between 2 points. So for example, in this condition, if you are in this condition, where you have Q3, which is less than the capacity of the bottleneck. Q3, which is less than the capacity of the bottleneck. So if you take this slope, okay, the sorry, yeah, this line. What does it have to do with Q3? So it's a slope between these two points. Okay, Q3 and Q2. Okay, it is a slope between these 2 points, Q3 and Q2. And if you take the slope between these 2 points, it will give you the velocity of the forward shock wave. Which one? This one. This one.
You take the slope between Q2 and Q3, and then you show the slope between Q1 and Q2.
Q1, Q2 is this one. Then see.
You want the slope between Q1, Q2 and Q3.
Yeah.
This one.
Q3. This is at Q3, not between Q1 and Q2. This one is between Q1 and this one. But you get the point. Forget about the lines. No problem. Okay. If you take the slope between Q3 and Q2, what is Q3? The flow which is entering the bottleneck, and this flow is less than the capacity. The flow is less than the capacity. If you take the slope between them, it will give you the velocity of the forward shock wave. Okay. Similarly, if you take the slope between Q1 and Q2, if Q1 is more than the capacity of the bottleneck, okay, then it will give you the slope will give you the velocity of the shock wave which is receding. Okay, we will talk about these things in detail. Okay, and what else? Okay, let me move forward. I think the other slides are more clearer. Okay, so shock waves can be of different types. Okay, shock waves can be of different types. We have looked at 2 or 3 of them in the last graph. So we have frontal stationary shock wave. One of them is frontal stationary shock wave. This shock wave happens when the capacity reduces suddenly to 0. When the capacity reduces suddenly to 0. So you are coming on a highway and the capacity of the highway becomes 0. And when can this happen? At a red signal. Okay. Other things I have mentioned. Maybe there is a very serious incident which has blocked the entire highway. So frontal means that there is a stop line or there is a point after which nobody is going forward. So that's why they call it frontal shock wave. So everybody comes to this front line and stops. Okay. Okay. Then we have backward forming shock wave. Okay. The backward forming shock wave happens when the capacity reduces below the demand flow rate which is coming from the other side. Okay, backward forming shock wave happens when the capacity is less than the demand which is coming from the previous segment. Okay, which case is this one from the last graph? Huh? Bottleneck. Which one was that? Q1 and Q2. Q1 and Q2. Q1 was more than capacity, right? Okay. So Q1 was the demand and the capacity was Q2 only. So that one is backward forming shock wave. Backward forming shock wave. Now what will happen in this case? Capacity is not 0. There is the capacity. Okay. So people are moving, but not at the rate at which they are coming. So they are moving forward, and at the same time the queue is also forming. Okay, so that's why they call it backward forming. Okay. Yeah. So the shock wave, meaning the queue is moving backward. The flow is moving. If you look at the flow, you will see the vehicles are moving. But if you look at the queue, you will also see that after every few minutes the queue is getting longer and longer. Okay. So it can happen at approach of a signal intersection. Signal is red. I think this is a mistake. I should have deleted it. Or at a location of the highway where the number of lanes are reduced. Okay. So red signal is frontal shock wave. Okay, you can cross it out. Okay, then we have backward recovery shock wave. Backward recovery shock wave is formed when the demand flow rate becomes less than the capacity of the bottleneck. So which case is this from the graph? Huh? Q2 after, yes, you can say this, or Q3. Okay, so there the demand flow rate, okay, but the demand flow rate has become less than the capacity of the bottleneck. Okay, So it was Q1. Now from Q1 it has gone to Q3. It was more than the capacity. Now it is less than the capacity. Okay. So that's why we call it recovery. Because what will happen now? What will happen?
Vector will move faster.
They will move faster. So what are you recovering now? The Q. Because will move faster, that means the Q is getting now smaller and smaller. Okay, so that's why we call it recovery. Okay, and it can happen when you have removed the restriction from the road. So there was a restriction on the road, maybe number of lanes were blocked, maybe there was a red signal. If you have removed these things, the lanes are open, the signal is green, then you will have a backward recovery. Okay, so you will see the cars are moving from the front faster and the queue at the back is getting smaller and smaller. So that's why we call it backward recovery.
This sudden increase in capacity.
Increase in capacity. Okay, increase in capacity or reduction in demand, anyways. Okay, the demand is less and capacity is more. Then we have the recovery. Then we have the rear stationary and forward recovery shock waves. Okay, so those two happen one after another. These two shock waves happen one after another. So demand for a upstream. Upstream means what? Upstream means before. The segment before is called upstream. So if I say upstream of bottleneck, that means before bottleneck. Okay, so demand before bottleneck was higher than its capacity, and then it became equal to its capacity, not less, equal. The initial demand was higher than capacity, and then it reduced to capacity, exactly. Then you will have this phenomena which is known as rear stationary and forward recovery. Okay, so what will happen? What will happen initially? When demand is more than capacity, what will happen? You will have a Q. Okay, and then when the demand becomes demand becomes equal to capacity, what happens?
The Q is still same.
It's the same now, but everybody is moving now in a stable manner. Okay, the Q will not reduce or increase, but everybody is now moving in a stable manner. Okay, so maybe there is a 4-lane highway, one direction, and it is leading to a two-lane tunnel. Okay, but you need to keep in mind the relationship between demand and capacity. Okay, in all cases, just keep in mind the relationship between demand and capacity. Okay, this diagram is showing a bottleneck on both sides. Okay, so you have more capacity here, then a bottleneck, and then you go forward, and then you have the same phenomena on this side. Maybe it's a tunnel or a bridge which has less number of lanes as compared to this one. Okay, so they are trying to show you the different types of shock waves. Okay, so because of anything, there is a stoppage here, then there will be a frontal shock wave. If I put a signal here, or I block these lanes because of any reason, then there will be a frontal shock wave. When I open this, then it will be backward forming shock wave. So if I remove the signal or whatever restriction there was, if I remove it, then it will be backward forming shock wave. Okay, and if the demand coming from this side is more than the capacity, and then it becomes equal to the capacity, then these two will happen. Forward recovery and rear station. Okay? Clear? Okay. So, now tell me, if the capacity becomes 0, which type of shock wave we have? Capacity becomes 0. Which shock wave we have? Frontal station. Okay. If the capacity is less than the demand, there the capacity was less than the demand, which type of shock wave we have? Backward, which one? No. We are not recovering, right? Are we recovering something? Demand is less than, demand is more than capacity. Sorry, demand is more than capacity. So which type of shock wave we have? Backward forming. Okay, backward forming. And then if you have so if you what will happen? Which type of shock wave we have here? So it was less, and now you are clearing the bottleneck. So now we have recovery, the backward recovery. Okay, and then we have the other two types of rear stationary and forward recovery. That happens when the demand was more than capacity, then it become equal to capacity. Okay, now what is important for us as traffic engineers? What is important for us as traffic engineers for shock waves? The important thing is velocity of the shock wave. Okay. Now, what do we mean by velocity of the shock wave? Velocity of what? When shock wave happens, what indicates a shock wave? Speed. Q forming. The main concern for us is the Q, the length of the Q. Velocity of the shock wave is basically how quickly the Q will increase or decrease. This is the velocity of the shock wave. How quickly the Q will increase or decrease because of the shock wave. This is our main concern, and this is the velocity of the shock wave. Okay, so let's say, I hope the slides on the blackboard are much clearer. It is messing up with the notations here, but anyways. So we have two segments here. Okay, in the first segment, the velocity is u1 and the density is k1. This is velocity of traffic flow. Keep in mind, there's a difference between them. Velocity of shock wave is different, velocity of traffic flow is different. Okay, so in the first segment, which is segment P, the space free speed is u1 and the density is k1. You reach line W or point W, after which there is a bottleneck. Okay, so the bottleneck segment is Q. Okay, so in this segment, the velocity is u2 and the density is k2. Clear? Okay. Now velocity of the shock wave is uw. Okay, so the shock wave or the Q will increase with the speed of uw. Clear? Clear? If I look at this segment, if I look at the cars in this segment, they are moving at an average speed of. If I look at the cars in this segment, they are moving at an average speed of uw. Uw is the effect of this bottleneck, which is happening where? In which direction? This direction or this direction? Forget about that. Forget about that. Where is the effect of this shock wave? Backward. Because of this W point, you will start to have a Q from this backwards, right? Okay, so maybe earlier there are only 10 vehicles in the queue. If this happens for 1 hour more, maybe you will see 50 vehicles in the queue. Okay, so the queue will increase. That is uw. Okay, now if the shock wave is going backwards, why are we showing it with uw with the front sign, with the front arrow? Why is that? You have taken shear force bending moment, right? Huh? So you put notations. Huh? Which direction shear force is taken positive? Normally. Huh? Up. Is the shear force always upwards? No, right? So if it is downward, then you put what? Negative sign. So this is what you will do. Okay, this is just our notation. The front arrow is just our notation, but we know the shock wave can be backward or it can be forward. It can happen both ways. Okay. In this case, it is happening backwards. Okay, because there is a reduction in capacity. Okay. Now, UR1. Let me. UR1. UR1 is the relative speed of vehicles compared to the shock wave. U1 is the speed of the vehicles and UW is the speed of the shock wave. Okay, so the difference between them is called as a relative speed. Okay. Now we know there is a relationship Q equals K into U. So Q equals Q, right? Q equals Q. Okay. Here K equals to K1, U equals to U1. So Q1 equals to K1. There. Okay. And yes. So if this is my Q1, what was Q1? What is Q? Flow, right? Flow. What are the units of flow? Meter per hour, right? Now if I ask you for number of vehicles, what would you do? Number of vehicles. You have vehicles per hour, you want number of vehicles. What do you do? Multiply by time, right? Okay, so this is what that means. N1 is number of vehicles which is going from here to here. Okay, so you already have the flow. So this will be UR. Okay, because there is a shock wave, so you cannot take the speed directly. Okay, so this. Okay, if it was without shock wave, I'll put U1 here. Because there is a shock wave, I cannot put U1. Okay, so I will take the relative speed. So this is number of vehicles which are going from here to here. Okay, I'll apply the same thing to segment Q now. Okay, so the relative speed in segment Q is UR2. What is relative speed? So instead of U1 now it will be U. Okay, so this is. If you want number of vehicles which are passing from segment Q, I'll do the same thing, right? Instead of UR1 now it will be UR2. Instead of K1 it will be K2. What about time? Same. Okay, so N2 equals UR2 K2. Clear? Okay. Now number of vehicles going from here to here and number of vehicles moving forward, they should be same, right? If 100 vehicles enter, then 100 vehicles will leave. Clear? So N1 equals to N2. Okay. What is N1? This thing. What is N2? This thing. I will make them equal. Okay. So when you make them equal, and then we have, then we also know UR2 equals to what? This U2 minus W, right? And UR1 equals to what? U1 minus U2. Okay. So u2 okay, the relative speed in segment 2, the relative speed in segment 1, because you are 2, you are 1, I change them into their equations, so t will cancel out. Okay, I am trying to drag the equation for what, which is what, uw. Okay, so you take uw on one side, everything else on the other side. I am writing the final equation, which is uw equals q2 minus q1 okay, clear? Okay, so I have two segments. One segment velocity u1, density k1. Another segment velocity u2, density k2. I found the relative speed in both of them. Then I found the number of vehicles in both of them. Number of vehicles should be equal, so I made them equal. Okay, and this is the final equation we have. Okay, uw, look at the notation. In this case, will it be positive or negative? uw. Negative, because my rotation is what? This side, but the shock wave is happening other side. Okay, what type of shock wave is this? Backward forming. Very good.